It has a name whose real meaning will be, you will understand later on. Sets are partially ordered by set inclusion. What is the meaning of being partially ordered? We will come to that later when we see partial order relations. Set inclusion is nothing but this relation is a subset of that, has another name that is called set inclusion. Okay. And this relation has been defined on the class of all sets. So what does this mean? Let A, B and C be sets, then the following are true. If A is a subset of B and B is a subset of A, then A is equal to B. Next, if A is a subset of B and B is a subset of C, then A is a subset of C. You may recognize this condition as the one we have when we discussed equality of sets, namely transitivity. We will see general discussions about these things, okay, later on. Now this is exercise. This appears as the fourth exercise. This one, however, we have to prove, although the proof is extremely easy, but we will solve this as exercise 314 when we solve the exercise problems. Okay, we'll leave it now. Remark. There is a relation between union and set inclusion. See exercise 317. See, we said that union is like addition, right? And inclusion relation is like this relation. And we already know that there is a relationship between these two things, which we have discussed in one of the results involving the net system of natural numbers, which just simply says that if A, B and C are, if A and B are two natural numbers, no, I think we need three natural numbers. A, B and C are three natural numbers and A is less than or equal to B, then A plus C is less than or equal to B plus C. There is something similar involving union and set inclusion. That we will see that in exercise 317. Okay, so that is the remark, 19th item. Then we have remark 3.1.20. These remarks make things much more clear and make the discussion richer. Okay, now this is a more important remark. So there is an important distinction between the relations this and this. Well, these are somewhat special. I mean, this is less than or equal to, instead of that we have strict inequality. Here we can call this strict inclusion. Okay, this is inclusion, this is strict inclusion. In this example, these two sets are related by strict inclusion actually. So what is the distinction between these two? The distinction is totality. For any two natural numbers A and B that are distinct, that is A is not equal to B, we have A is less than B or B is less than A. This was the result that is called trichotomy. It was proposition 2 to 13. Okay, this we already know. If we take two distinct natural numbers, then one is strictly less than the other. However, if we are thinking of this relation behaves in much the same way like this one. However, this is the distinction. This is not the case with sets. However, given distinct sets, A and B, it's not necessary that we have either this or this. For example, let A be the set of all even natural numbers. Okay, natural numbers which look like this, 2 and 2 times some other natural numbers, and B to be the set of all odd natural numbers. Then you already know that neither of them is a proper subset of the other. Then we have neither this nor this. So that is why we say that set inclusion or proper inclusion orders the class of sets partially, not totally. Not, I mean, if any two elements are given, and if any two numbers are given, they are comparable using this relation. However, if any two sets are given, they are not necessarily comparable. That's why sets are partially ordered but numbers are totally ordered by the respective relations, order relations. In this regard, see definition. We will see these things when the time comes. See definition 851. Definitions 851 and 853. In 8th chapter, we are going to see infinite sets, axiom of choice, and other such advanced topics in set theory. There is one remark after this. We have already discussed this particular aspect of sets. A great confusion